Soft PDF link is in the description and in the comment pin, and also there is a video that how to download the soft PDF. Video we'll be discussing about atomic structure from physical chemistry. So atomic structure. Now inside the nucleus of an atom there is proton and neutron, and outside the nucleus in the electron shell there is electron. So proton, neutron and electron, what is the charge? Proton has a charge of +1, neutron has a charge of 0, while electron has a charge of -1. So proton +1, neutron 0, electron -1. Then for mass, proton has a mass of 1, neutron has a mass of 1, and electron has a mass of 1 by 1840. So proton has a mass of 1, neutron has a mass of 1, and electron has a mass of 1 by 1840. Then atomic or proton number. So atomic or proton number is the number of protons, and nucleon or mass number is the number of protons plus neutrons. So nucleon or mass number is the number of protons plus neutrons. Then isotopes. Isotopes are the atoms of the same element. So they are the atoms of the same element. Same element having the same number of protons and electrons but different number of neutrons. So they are the atoms of the same element. Atoms of the same element having the same number of protons and electrons but different number of neutrons. So isotopes have different number of neutrons. Isotopes have different number of neutrons. Then isotopes have same chemical properties. Same chemical properties means that they have the same number of protons and electrons, and since protons and electrons determine the chemical properties, so since they have the same proton and electron, so they have the same chemical properties. But isotopes have different physical properties. Isotopes have different physical properties, and physical property is such as like mass or density. And since isotopes have different number of neutrons, so isotopes have different number of neutrons. Therefore, isotopes have different mass number or nuclear number. So isotopes have different mass number of or nuclear number due to different number of neutrons. Since they have different number of neutrons, so they have different number mass number or nuclear number due to a different number of neutrons. And so since they have different number of neutrons, so the mass of isotope varies. That's why they have different physical properties such as mass. Then shell, subshell and orbital. So suppose for this atom there is 1, 2, 3 shell. These are shells, and the shells are further divided into subshells. For example, we have 1s subshell, then 2s 2p subshell, then 3s 3p subshell. These are the subshells, and the subshells are further divided into orbitals such as SPDF. So SPDF. For example, this is an s orbital, then p subshell has 3 orbital, that is px, py and pz orbital. So p subshell has 3 orbital, px, py and pz orbital. Then p subshell has 3 orbital, px, py and pz orbital. And so for shell, subshell and orbital, there is 1, 2 and 3 shell. Now shells are divided into subshell, that is 2s2 and 2p6. These are the 2 subshell. Then 3s2, 3p6. These are the 2 subshell. And the subshells are further divided into orbitals, that is, this is an orbital, that is px, py and pz. And each orbital must contain 2 number of electrons. That is, orbital has 2 electrons. For example, this orbital has 2 electrons. Then this orbital has 2 electrons, and these arrows are showing the number of electrons. And orbitals fill in the orders such as, like for a p orbital, suppose there is 5 electrons. So the electrons fill in the order that 1 electron, then another electron, then another electron. Now we have arranged 3 electrons. Now we need 2 more electrons. So 1, 2. So electrons fill in this order. And for d subshell, so how the electrons are arranged in the orbitals? For example, d subshell has 5 orbitals. So 1, 2, 3, 4, and this is our 5. So for these 5 orbitals, and also you need to remember that S subshell contains a maximum of 2 electrons, P subshell contains a maximum of 6 electrons, and D subshell contains a maximum of 10 electrons. So S has 2 electrons, P has 6 electrons, and D has 10 electrons. And let's suppose we have about 6 electrons left to fill the D subshell. Then the electron arrangement would be 1, 2, 3, 4, 5, and then 6. So this is the electron arrangement. That's how we show the electron arrangement. And for calcium 20. So calcium 20, and so first of all, the electrons fill in this order, that is 1s, then 2s, then 2p 3s, then 3p 4s, then 3d 4p, like this order. So 1s, then 2s, then 2p 3s, 3p 4s, 3d 4s, this order. So for calcium 20, so it has 20 electrons. So S subshell has 2 electrons, that means 1s2, then 2s2, 2p6, 3s2. So 3s2, then 3p6, then 4s2. So if we count, then 2, 2, 4, 6. So 4 plus 6, 10, 12, 18, and 20. So in total there is 20 electrons, and this arrow shows the number of electrons. There is 20 electrons. Thus, orbitals have a maximum number of 2 electrons. For example, this is an orbital, it has 2 electrons, and let's suppose this is an orbital, it has a maximum number of 2 electrons. For example, this orbital, this can contain a maximum number of 2 electrons, but now it has 1 electron. So if let's suppose there is 2 electrons, so orbitals can contain a maximum number of 2 electrons. And including the orbitals, we have px, py, and pz and s orbital. So px, py, and pz and s orbital, and D subshell has 5 orbital. It is 1, 2, 3, 4, 5. So 5 orbitals, and we don't need to remember its name. We just refer this as D orbital. Then for the orbitals, if we need to draw, then for s orbital is circular in shape. So first of all, determining the axis. So this is the x-axis, then this is our y-axis. So remember that this is our y-axis and this is our z-axis. So S subshell is usually round, S orbital is usually in round shape. So S orbital round shape. Then for the axis, that is x-axis, y-axis, and z-axis. So px orbital. Now px orbital is in the x-axis. Then py orbital is in the y-axis. Then pz orbital is in the z-axis. So you need to remember these diagrams for the periodic table. This is the S block element that also includes hydrogen and helium. So S block element, then this block is the P block element, and this block is the D block element. So according to our instruction, this is our S block element, that is hydrogen, helium, and this block, these are our S block elements. Then this is our P block element. So this is our P block elements. So this is S block, this is P block, and this is our D block element. So these are our D block element, that is D block, and these are F block. So you don't need to remember the F block right now. Then for determining the electronic configuration, so including the elements, let's choose any random element. Let's suppose nitrogen. Then for nitrogen, what would be the electronic configuration? So nitrogen has 7 electrons, so it would be 1s2, 2s2, 2p3. That means 1s2 has 2 electrons, 2s2 has 2 electrons, and 2p3 has 3 electrons. So 2 plus 2 plus 3, that is 7. So 7 electrons. Then for oxygen has 2, 4, 8 electrons. So 8 electrons. Then for, let's suppose silicon has 14 electrons. So 1s2, 2s2, 2p6, 3s2, 3p2. There is 2 plus 2 plus 6 plus 3 plus 2 plus 2. So 2 2s are 4, 10, 12, 14. So 14 electrons. Now for chlorine has 17 electrons. So 1s2, 2s2, 2p6, 3s2, 3p5. Then 2 electrons, 2, 6, 2, 5. So 2 2s are 4 plus 6, 10, 12, 17 electrons. So now, how can we determine the electronic configuration easily from the periodic table? Let's suppose we choose any random element. Let's suppose we choose chlorine. So chlorine is in period 1, 2, 3. So it is in period 3. That is period 1, 2, 3. So chlorine is in period 3, and we remember that it is the p block element. So p block element. Now from this p block, it is the first, second, third, fourth, fifth element. So 3p5. That means it has a valence electron in 3p5 subshell. So for chlorine, the valence electron is in 3p5 subshell, and according to the order, we arrange this until we reach 3p5. So until we reach 3p5. Then let's suppose any S block element. Let's suppose any S block element. Let's suppose magnesium. So for this magnesium, so this is in period 1, 2, 3. So magnesium is in period 3. So 3, and it is the S block element. So S, and it is the second element of the S block. So 1, 2. So second. That means its valence electron is in 3s2 subshell. Now magnesium has valence electron in 3s2 subshell, and since it has 12 electrons, so we arrange this until we reach 3s2. That is 1s2, 2s2, 2p6, 3s2. Now let's suppose another element. Let's suppose phosphorus. So, and also you need to remember that the electron arrangement occurs in this way. That is 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, like this order. Now we are discussing phosphorus. So phosphorus, for phosphorus, it is in period 1, 2, 3. So it is in period 3, and it is p block element. So p block, this is S block, this is D block, and this is p block. So p block element, and this is the third element of the p block, that is first, second, and third. So 3p3. That means it has a valence electron in 3p3 for phosphorus. So phosphorus has a valence electron in 3p3 subshell, and the electron arrangement occurs in 1s2, 2s2, 2p6, 3s2, 3p3. And you also need to remember that S subshell contains a maximum of 2 electrons. So regarding all the examples, S subshell has a maximum of 2 electrons, P subshell has a maximum of 6 electrons. So regarding the options or the examples, P subshell has a maximum of 6 electrons, and we will discuss that D subshell has a maximum of 10 electrons. And let's suppose another element. Let's suppose we consider fluorine. So fluorine. So for this element fluorine is in period 1, 2. So period 2, then it is the p block element. So p block, and it is the first, second, third, fourth, fifth. So it has the valence electron and in 2p5 subshell. So for fluorine, the valence electron is in 2p5 subshell, and the electron arrangement would be 1s2, 2s2, 2p5. Now for an element such as bromine. So bromine has 35 electrons. So this is our bromine, and bromine is in p block. So first of all, it is in period 1, 2, 3, 4. So it is in period 4. Then it is a p block element, so p, and it is the first, second, third, fourth, and fifth. So it is the fifth element of the p block. So this is our p block, and this is the fifth element of the p block. So 4p5, that means it has a valence electron in 4p5. So bromine has a valence electron in 4p5. Now, to determine the electron arrangement, we need to follow the sequence. That is 1s, 1s2, then 2s, so 2s2, then 2p, 3s, so 2p6, 3s2, then after 3s2, it is 3p6, so 3p6, then 4s2, and after 4s2, according to the sequence, we can see that it is 3d, so 3d10, then 4p5. So we know that the valence electron is in 4p5. So this is our electron arrangement, and we need to follow the sequence. That is, for this sequence, you need to remember the sequence. And after 4s, we can see that after 4s2, it is 3d10. So it is 3d10. Then after 3d10, it is 4p5. So 4s2, 3d10, then 4p5. 4s2, 3d10, 4p5. And that's how we show the electron arrangement. And this refers to our electrons. So that's how we show the electron arrangement. Then let's suppose for the D block element, such as zinc, there is a little variation. Now for the D block element such as zinc, so zinc is the D block element, that is, it is S block, this is P block, and this is D block. So zinc is in D block element. And so for the D block element, so zinc is in period 1, 2, 3, 4. So it is in period 4. So instead of writing our answer in terms of 4, we need to subtract the 4 by 1. That is, it is in, we need to consider a value that is 3. So it is in period 4, but we need to subtract 1 and we need to consider the value as 3. So 3, and it is the D block element, so 3D, and this is our D block. So this is our D block. Then for this D block element, this is our D block. So for this D block element, zinc is in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is in 3D 10. So zinc has the valence electron in 3D10 subshell. Zinc has a valence electron in 3D10 subshell, and you need to follow the sequence. That is 1s, 2s, 2p, 3s, 3p, 4s, then 3D10. So it has a valence electron in 3D10. So 3D10 for zinc, and let's suppose for another D block element such as iron. So iron, let's suppose this is our iron. So iron is in period 1, 2, 3, 4. So it is in period 4. But instead of writing 4, we need to subtract 1 and we get a value of 3. So 3. Now it is D block element, so 3D, and it is in period 1, 2. Okay, so we have discussed this. So 3D. Now from this D block, it is the first, second, third, fourth, fifth, sixth. So it has a valence electron in 3D6 subshell. So now we can see that iron has a valence electron in 3D6 subshell, and 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 until we reach a value that is 26. So 26, that is the number of electrons, that is 26, and it is in 3d6. Now for iron 3 plus ion. So iron 3 plus ion. So first of all, we discuss the ions later. Now for copper and chromium, there is a little variation. That is from the D block. For copper and chromium, there is little variation. So for copper and chromium, so first of all, let's determine the electron. And so for chromium, so first of all for chromium, so chromium is in period 1, 2, 3, 4. So period 4, but instead of writing 4, we need to subtract 1 from this value. So now we consider the value of 3. Now 3, and it is our D block element, so 3D. So this is D. So 3D, and it is the first, second, third, fourth. So fourth element of the D block. So now we should have a value that is 3D4. So for chromium, we should have a value that is 3D4. But instead of writing the answer as 3D4, we have written this as 3D5. Because now here we can see that for both the electronic configurations, the number of electrons is same, that is 24. So this has 24 electrons. This has also 24 electrons, since this is chromium. So chromium, but here we can see that there is 1 electron from 4s subshell is transferred to 3D5, 3D4 to convert this to 3D5. For example, for this D block, there is 1, 2, 3, 4, and 5. So for this D block, chromium has the valence electron in 3D4 subshell. So 1, 2, 3, 4. But instead of writing this as 3D4, we write this as 3D5. That is, we add 1 valence electron from the 4s subshell. So instead of writing as 4s2, we write this as 4s1 and 3D5. So for chromium, you need to remember this. This is the exception for only for chromium and copper. So for chromium, first of all chromium, instead of writing 4s2 and 3d4, we write this as 4s1 and 3d5. So 4s1 and 3d5. That means the number of electrons are same, but we differ the variation. Just there is a little variation. You need to remember this. And for chromium, so for copper, copper is in period 1, 2, 3, 4. Copper is in period 4, but instead of writing 4, we need to subtract 1 since it is a D block element. So for the D block, we need to subtract the value by 1. So this is only for the D block that we need to subtract the value by 1. So 4 minus 1 is 3. So now it is in 3 and D block, so D, and it is in 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3D9. So it has a valence electron in 3D9 subshell. So copper has a valence electron in 3D9 subshell, But instead of writing this as 4s2 3d9, we write this as 4s1 and 3d10. So instead of writing this as 4s2 3d9, we write this as 4s1 3d10. So this is a quite little variation, that the d block contains either 5 or 10 electrons instead of 4 or 9 electrons. So you need to remember this. This is important. 10 electronic configuration. So let's suppose for iron. So iron is in period 1, 2, 3, 4. So it is in period 4, but instead of writing 4, we need to separate the value by 1, so that is in 3. And it is a d block, so 3d. So this is 1, 2, 3, 4, 5, 6. So it has a valence electron in 3d6 subshell. And according to the sequence, we write the values, that is 1s2 2s2 2p6 3s2 3p6 4s2 3d6. So this is our electron arrangement, and instead of writing the total electron arrangement, we have shortened this, that is, before iron, the only noble gas that comes is argon. So instead of writing the total electronic configuration, we write this as argon. That is, argon has 18 electrons, so we don't need to write the 18 electrons in the order. So argon, that means argon has 18 electrons, so we don't need to write the 18 electrons in the order. That is, instead of writing this 18 electrons, we write this as in terms of argon, since it has 18 electrons, and then after writing argon, we write this as 4s2 3d6. So 4s2 3d6. This is our shortened electronic configuration. Okay, so then free radical. So free radical is a species that has one or more unpaired electron. So you need to remember the statement that free radical is a species with one or more unpaired electron. So one or more unpaired electron. So free radical is a species with one or more unpaired electron. Now for the shortened electronic configuration, again, if we just look at, so for the examples we have given, let's suppose the shortened electronic configuration for zinc. So for zinc, so zinc is the d block element, and it is in period 1, 2, 3, 4. So it is in period 4, but instead of writing 4, we separate the value by 1, that is 3, and it is a d block element, so 3d, and it is first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. So it has a valence electron in 3d10, and for the shortened electronic configuration, it has a noble gas before it is argon. So for zinc, it has a valence electron that is in 3d10, so 3d10, and before the zinc there is argon, so argon has 18 electrons, so 18 electrons, 3d10 has 10 electrons, so 10 electrons, and 4s2 has 2 electrons. So in total we can see that the combined answer is 30 electrons. So this is the electronic configuration for zinc. There is a shortened electronic configuration showing the 30 electrons, but instead of showing the first 18 electrons, we write this as argon. So for after zinc, let's suppose we discuss another elements. Let's suppose it is calcium. So this is only for shortened electronic configuration. Now for calcium is the S block element, and this is in period 1, 2, 3, 4. So it is in period 4. So period 4, and since it is a S block element, so we don't need to separate 1. So it is in period 4, then 4s, and it is first, second. So second element. That means it has a valence electron in 4s2. And before calcium, there is argon as the noble gas. So argon has 18 electrons and 4s2. That is for calcium, argon has 18 electrons, so 18, and 4s2. So 4s2 has 2 electrons. So in total there is 20 electrons. That's how we write the shortened electronic configuration. And if we just again revise, then for copper, you need to know that copper and chromium has a little variation. So copper is in period 1, 2, 3, 4. So instead of writing 4, since it is d block, so we need to subtract 1. That is, we need to consider the value as 3. Then it is the d block, so 3d. And this is the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth. So 3d9. That means it has a valence electron in 3d9. But instead of writing 4s2 3d9, that is, instead of writing as 4s2 3d9, we write this as 4s1 3d10. So 4s2 3d9, instead of writing this, we write this as 4s1 3d10. So 4s1 and 3d10. And for copper, before copper, the noble gas is argon. So argon has 18 electrons, 3d10 has 10 electrons, and 4s1 has 1 electron. So in total we get a number of electrons as 29. So 29 electrons. Now for again, if we just look at another element, let's suppose chromium. So you need to remember the variation for chromium. Instead of writing 4s2 and 3d4, we write this as 4s1 and 3d5. So chromium is in 1, 2, 3, 4. So it is in P4. So instead of writing 4, we need to separate the value by 1, that is 3. Then it is the first, second, third, fourth. So it is the D block and 3d4 since it is the fourth element. Then it has a valence electron in 3d4. But instead of writing 4s2, 3d4, we write this as 4s1, 3d5. Instead of writing 4s2, 3d4, we write this as 4s1, 3d5. And this variation is only for copper and chromium. So for chromium, it is 4s1 and 3d5. Now for the ionic radius, so first of all, here we can see that the numbers are arranged in the sequence. That is, first of all 3, then 4, then 4p, then 5, 6, etc. So these are arranged in the sequence, that is 3, 4, 5 in the numerical order. So to determine the ionic radius, first of all we need to arrange this in terms of ionic. First of all we need to arrange this in the numerical order, or so now if we just arrange in terms of order, numerical order, there is 1, then 2, then 3, then 4. So now here we can see that for iron 3 plus ion, the 2 electrons are lost from 4s2, then so 2 electrons are lost and 1 electron is lost from 3d6 to become 3d5. There is 1 electron is lost. That is, a total of 3 electrons are lost to form iron 3 plus ion. That means now it has a valence electron in 3d5 subshell. So 3d5 subshell. So instead of writing this in terms of order, you can also write this that 4s2 loses electrons first, then 3d6 or 3p6. Similarly, for zinc 2 plus ion, so for zinc 2 plus ion, so first of all, 2 electrons are lost from 4s2, then so we have lost 2 electrons. So this is the final electronic configuration for the zinc 2 plus ion. That is, all are arranged in the numerical order. And let's suppose for another element such as calcium. So for calcium 2 plus ion, that means it loses 2 electrons from 4s2. Then K plus ion, so potassium loses electrons from 4s1, there is 1 electron, and this would be the final electronic configuration. Energies. So first ionization energy. So first ionization energy, suppose for sodium in gaseous state. So sodium forms sodium plus ion and 1 electron is removed. So first ionization energy. So first ionization energy is the energy needed to remove 1 mole of electron. So energy needed to remove 1 mole of electron, that is to remove 1 mole of electron from 1 mole of gaseous atom. So the atom must be in gaseous state and not in the solid or in the liquid state. So the atom must be in gaseous state. So to remove 1 mole of electron from 1 mole of gaseous atom to form 1 mole of gaseous 1 plus charge ion, to form 1 mole of plus 1 charge gaseous ion, that is 1 plus gaseous charge ion. So what would be the ionization energy? Ionization energy is the energy needed to remove 1 mole of electron. Energy needed to remove 1 mole of electron. There is 1 mole of electron from 1 mole of gaseous atom. So the atom must be in gaseous state to form 1 mole of 1 plus gaseous 1 plus charge gaseous ion. To form 1 mole of plus 1 charge gaseous ion. So this is the first ionization energy. There is the energy needed to remove 1 mole of electron. Energy needed to remove 1 mole of electron. Energy needed to remove 1 mole of electron from 1 mole of gaseous atom. So from 1 mole of gaseous atom, and the atom must be in gaseous state, not in the solid or in the liquid state, to form 1 mole of gaseous 1 plus charge ion. To form 1 mole of gaseous 1 plus charge ions. So this is the equation for the first ionization energy. There is sodium in gaseous state to form sodium plus ion in the gaseous state, and 1 electron is removed for the first ionization energy. And the atom must be in gaseous state, not in the solid state. It would be wrong because it would not be the ionization energy. Then for the second ionization energy, for all the ionization energy, the atoms must be in gaseous state. So the atoms must be in gaseous state. That is, for the second ionization energy, So for second ionization energy, this is for the first ionization energy. And after first ionization energy, we get sodium plus gas as the product. So sodium plus gas, it loses another electron to form sodium 2 plus gas. Then for the third ionization energy, so the product is sodium 2 plus gas. So sodium 2 plus gas loses one electron to form sodium 3 plus gas. That means as the ionization energies are increased, one electron is removed. That is for the first ionization energy, it forms sodium plus ion. Then sodium plus ion reacts to form sodium 2 plus ion for the second ionization energy. And for the third ionization energy, sodium 2 plus ion forms sodium 3 plus ion. And it all of this removes 1 mole of electron to form 1 mole of gaseous charge ion. Then for successive ionization energies, let's suppose for sodium. So for sodium, the ionization energy is on the y-axis and the number of electrons is on the x-axis. So on the x-axis there is number of electrons and on the y-axis there is energy. So energy and electrons. So for sodium, the first electron is from 3s subshell. So first electron has less energy. Then for the second shell, that is second shell, that is 2s2 and 2p6. So second shell has 2s2 subshell and 2p6 subshell. That means in total there is 8 electrons. And so since it is closer to the nucleus than compared to 3s, so more energy is needed to remove these electrons. That is 1, 2, 3, 4, 5, 6. That is for 2p6, then for 2s2. Since 2s2 and 2p6 are close together, so their ionization energies are approximately close together. But since 3s, 3 and 2 are further apart, so this is for 3 and this is for 2. So they are further apart. But for 2s and 2p, they are close together, so the ionization energies are also close together. Thereafter 2, the one subshell or one shell is closer to the nucleus. Since this is the nucleus and one is closer to the nucleus than compared to 2 and 3, so since one is closer to the nucleus, so more energy is needed to remove the electron. Therefore from 1, 2 electrons are removed and this has the highest energy. Then for the ionization energy, you need to remember that ionization energy increases across the period. That means as we go across the period, the ionization energy increases, and also the ionization energy increases up the group. Now for the ionization energy, we discussed that the ionization energy increases up the group. That is, up the group, the ionization energy increases, and across the period, the ionization energy increases. That is, ionization energy increases up the group, and ionization energy increases across the period. So ionization energy increases across the period and increases up the group. Then factors that influence the ionization energy. So factors that influence the ionization energy. Nuclear charge. Nuclear charge means that as nucleus contains protons and neutrons. So neutrons has no charge, but proton has a charge. That means as the number of protons increases, the nuclear charge increases. And as the nuclear charge increases, so the nucleus has a more charge. Now this nucleus would attract the valence electron with a greater force. This nucleus has more charge, and so this nucleus would attract the valence electron with a greater force. So the attractive force between the nucleus and the valence electron increases. Attractive force between the nucleus and the valence electron increases. And since the force of attraction increases, so the ionization energy also increases. Since the ionization energy is the energy needed to remove 1 mole of electron from 1 mole of gaseous atom. So as the attractive force increases, so since the attractive force between the nucleus and the outer electron increases, so more energy is needed to remove the electron. Since the attractive force increases, so more energy is needed to remove this electron. And since more energy is needed, so the ionization energy also increases. Again, as the nuclear charge increases means that the number of protons increases. And as the number of protons increases, so now the number of protons increases. So the number of protons increases means that the nuclear charge increases. So as the nuclear charge increases, the nucleus would attract the valence electron with a greater force. So the attractive force between the nucleus and the outer electron increases. Since the attractive force increases, so more energy is needed to remove the electron. more energy is needed to remove the electron, therefore the ionization energy also increases. Then for shielding, shielding is basically caused by the initial electrons. For example, this is the nucleus and this is the first shell and this is the second shell. Now here we can see that the first shell is full of electrons. So first shell is full of electrons. So here we can see that which has the most shielding. So here we can see that shielding is caused by the inertial electrons. So there is 1, 2, 2 inertial. While there is 1 inertial, so more shielding is in this nucleus. Since there is 2 inertials, so 2 inertial electrons. And since there is 2 inertial electrons, since there is 2 inertial electrons, so shielding by the inertial electrons increases. And as the shielding by the inertial electrons increases, so there is more inertial. That means the attractive force between the nucleus and the outer electron decreases. So we can easily tell that the attractive force between this nucleus and this outer electron is less compared to the attractive force between this nucleus and this outer electron. So this nucleus and this outer electron has more attractive force. So this atom has more attractive force. That means as the shielding increases, the attractive force between the nucleus and the outer electron decreases. As the shielding increases, the attractive force between the nucleus and the outer electron decreases, so the ionization energy decreases. And ionization energy is the energy needed to remove 1 mole of electron from 1 mole of gaseous atom to form 1 mole of gaseous ion. So as the shielding by the inertial electrons, so this is the shielding by the inertial electrons increases, the attractive force between the nucleus and the outer electron decreases. And as the attractive force decreases, the first ionization energy also decreases. Then distance from the nucleus or atomic radius. So distance from the nucleus or atomic radius. So suppose for this atom, here we can say the distance of the nucleus of the valence electron, that is the distance from the nucleus of the valence electron is this distance, while the distance from the nucleus to the valence electron is this distance. So here we can say the distance from the nucleus to the valence electron is more in this nucleus. So distance from the nucleus, or this is the atomic radius. So if we just consider this as the radius, since atom is a circle, so radius, so this is the radius. So here we can see that the distance of the outer electron from the nucleus, distance of the outer electron from the nucleus increases. As the distance of the outer electron from the nucleus increases, the attractive force between the nucleus and the outer electron decreases. So as the distance increases, the attractive force decreases. As the distance increases, the attractive force decreases. And since the attractive force decreases, so less force of attraction, so ionization energy also decreases. Since ionization energy is the energy needed to remove the electron, and since for this atom less energy is needed, so that means this atom can lose its electrons easily, so it has less ionization energy. Then for spin pair repulsion, so for spin pair repulsion, suppose for oxygen there is 8 electrons, so the electron arrangement would be 1s2 2s2 2p4, 1s2 2s2 2p4. Now for this electron arrangement, here we can see that it contains spin pair electrons. That is, if this is an orbital, then this is a spin pair electron. So this spin pair electron causes repulsion, and this electron, one of the electron can easily be removed due to this spin pair repulsion. So there is spin pair repulsion between the two electrons, and electrons in the same atomic orbital in the subshell repel each other more than the electrons in different atomic orbitals. So there is spin pair repulsion, and due to this spin pair repulsion, electrons can be easily removed. So energy needed to remove the electron decreases. Since electrons can be easily removed, so no energy is needed to remove the electron. Then the first ionization energy against the atomic number. So hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium. So we have discussed that as we go across the period, the ionization energy increases, and as we go up the group, the ionization energy IE increases. So as we go up the group, ionization energy increases, and as we go across the period, ionization energy increases. That means from hydrogen to helium, so from hydrogen to helium, as we go across the period, the ionization energy increases. So here we can see that the ionization energy increases from hydrogen to helium. Then from helium to lithium, the ionization energy decreases, and there is a larger decrease because as we go from helium to lithium, here we can see that the group decreases. And since as we go down the group, ionization energy decreases. As we go down the group, the ionization energy decreases, and so lithium has the least ionization energy compared to helium. So lithium has the least ionization energy compared to helium. Then after lithium, again we can see that the ionization energy increases as the period increases, or as we go across the period. So from lithium, as we go across the period, the ionization energy increases until we reaches the neon. So here we can see that from lithium, ionization energy increases until we reaches the neon. Then after neon, sodium. So sodium is in the next group, so the ionization energy decreases. So here we can see that after neon, just if we just clear this, then after neon, sodium is in the next group. And as we go down the group, ionization energy decreases. So sodium has the least ionization energy. So here we can say the sodium has the least ionization energy because we go down the group. So this is the first ionization energy against atomic radius. As we go across the period, the ionization energy increases, and as we go down the group, that means the ionization energy decreases. Then again it shows an increase, and as we go down the group, the ionization energy decreases. But as we go across the period, the ionization energy increases. That means this value and this value also should show the increase. That means it should show the increase in value. But why these two values decreases? By a slight amount or by a little amount. So if we just compare, then for beryllium, so now between beryllium and boron. So here we can see that beryllium has the valence electron in 2s subshell, while boron has the valence electron in 2p subshell. So as we can see that the valence electron is further from the nucleus in boron. So since the valence electron is further from the nucleus, so since the valence electron is further from the nucleus, or the distance of the nucleus from the valence electron increases, so the attractive force decreases and the ionization energy decreases. Since the distance of the nucleus of the valence electron, distance from the nucleus of the valence electron increases. So for boron, the distance from the nucleus of the valence electron increases by slight amount or by little amount. So the distance increases. Since the distance increases, so the attractive force decreases and the ionization energy decreases by little amount. So here we can see that the distance increases, so the ionization energy shows a decrease. So the ionization energy decreases, but since it is 2s and 2p, so there is a slight decrease. Then for nitrogen and oxygen, so now for nitrogen and oxygen, here we can see that both the electrons are in p subshell, but why oxygen value decreases? Why the ionization energy for oxygen decreases? Now this occurs due to spin pair repulsion, because if we just draw, then for nitrogen, if we just draw the p subshell, that means the electron arrangement in the p orbital. So here we can see that there is 3 electrons, so 1, 2, 3. But for oxygen, there is 4 electrons in the p subshell. So 4 electrons, so 3 boxes. So oxygen has 4 electrons, that is 1, 2, 3. And since oxygen has 4 electrons, so 4. Now here we can see that there is spin pair repulsion. So spin pair repulsion, so repulsion, electrons in the same atomic orbital causes repulsion, and due to this repulsion, the ionization energy decreases as the spin pair repulsion increases. So here we can see that the spin pair repulsion in oxygen, so the ionization energy decreases. Therefore, there is a little decrease in the ionization energy for oxygen. So that's how we draw the ionization energy, first ionization energy against atomic number graph.